Hello everyone and welcome to my video tutorial on Introduction to Graph Theory using Python and NetworkX. This is class 5 of a series, Optimization Involving Trees. My name is Innocent Okoloku. Motivation for the class today is that the concepts considered in this topic, they have very practical applications in many areas of science, engineering and the social sciences. Learning objectives. At the end of a class, participants should be able to define a tree, define the minimum weight spanning tree of a graph, describe the crosscast greedy algorithm, apply the crosscast greedy algorithm to calculate the minimum weight spanning tree of a graph, describe the Prim's greedy algorithm, apply the Prim's greedy algorithm to calculate the minimum weight spanning tree of a graph, describe the matrix version of the Prim's greedy algorithm, and apply the matrix version of the Prim's greedy algorithm to calculate the minimum weight spanning tree of a graph. Content: review of trees, minimum weight spanning trees, crosscast greedy algorithm, Prim's greedy algorithm, Prim's algorithm, matrix version. We begin with a review of trees. Recall from our previous classes that we described a forest, which is the same thing as an acyclic graph, as a graph that has no cycles, meaning that there is no loop in the graph. So when we say a graph does not have a cycle, we mean there is nothing like this. No loop. There is no way you can go around through a loop in the graph. That's what we mean by a graph with no cycles. So a tree is a graph that is connected and has no cycles. A spanning tree is a tree that contains all vertices of a graph and it has n-1 edges. So the way to remember what n is, it is the number of vertices in the graph. For instance, the graph we see below is one forest consisting of several trees and is disconnected. Even though it's one, it's a graph, it's disconnected. So the number of vertices here are 13. A forest is called greedy if there exists a minimum spanning tree of G that contains the forest. So let's talk about minimum weight spanning trees. First, we will recall we described a weighted graph before. A weighted graph is one in which every edge of the graph is assigned a real number as its weight. It may be the distance of a road, it may be the size of a pipe, or some other description. So a weighted network can either be a weighted graph or a weighted digraph. So the weight is usually written as a number on the edge or arc. The weight of a subgraph. If H is a subgraph of a weighted graph G, then the weight of H is the sum of all the weights of all the edges in H. A spanning tree T subscript S in a weighted graph is called a minimum weight spanning tree if among all the spanning trees of a graph, all the weighted spanning trees of the graph, this particular one is minimum. There is no other weighted spanning tree that is less than this. Then it is a minimum weight spanning tree. Meaning that it is possible that a graph can have several spanning trees. So next we are going to describe two greedy algorithms that we can use to obtain the minimum weight spanning tree of a graph. Why do we call them greedy? Because at every stage in the algorithms, a decision is made to select the best possible edge from the graph, either G or D, for inclusion in the minimum spanning tree. After making sure that the selection of an edge does not create a cycle in the subgraph already constructed. Let's see an example of an application of what we are talking about. So this is the city where I reside in at the moment, and this is a popular shop in town, and this is the airport. There are several roads to pass from the shop to the airport. If we know the distances, those are the weights of each of the edges. How can we decide which is the shortest route from this shop to the airport? That problem is akin to looking for the minimum weight spanning tree that connects the shop to the airport. So next we'll look at crosscars greedy algorithm. We'll describe the algorithm here. First of all, what crosscars greedy algorithm does is scan through the graph and give us a minimum weight spanning tree if it exists. So we'll call it algorithm crosscar, and the input will be our graph together with the edges, the weight of the edges or the length of the edges or whatever I want to describe it. So given a connected graph with edges having length Lij greater than 0, the algorithm determines the shortest spanning tree in G if it exists. So the inputs are the edges of G and their lengths. The output is the shortest spanning tree T in G, or a message that says it does not exist. First step, order the edges in ascending order of length as a list and choose them in this order as edges in T. You will only reject the edge if and only if the edge forms a cycle with the edges already chosen. If n-1 edges have been chosen and T does not exist, that is the minimum spanning tree does not exist, report that and stop. Maybe the graph is not connected. However, if n-1 edges have been chosen and T does exist, then output T, the set of chosen edges, and stop the algorithm. End crosscar. The algorithm is quite simple. So we see an example. Obtain the minimum spanning tree in the network below using crosscars algorithm. So we'll follow the steps. Step 1, we have to order the edges in ascending order as a list L, and this is what we have. So how do we order in ascending order? We look at the weights of the graph. The smallest weight here is 12 and it is duplicated. We can pick any one of them, but since 1 and 2 seems to be the starting point, we take 1 and 2 first, and then the next will be 3 and 4, which is equally 12. Then we have 13 here, which is the next small thing. So we can have 1 and 8 and 1 and 5, 4 and 5, both of which are equally 13. And then we have a lot of 14s here, so we can actually pick any one of them. So let's say we start from 2, 7, and then we have 3, 6, which is equally 14, and then we have 5, 6, which is equally 14, and then we have 7, 8, which is equally 14, and then we have 2 15s here, 6, 7, 5, 8, both of them are 15, and then we have 1, 4, and 2, 3, both of which are 16. The next step is to build the spanning tree. So like the algorithm says, we are just going to look at this sorted list that we already have here, and we start picking them one by one, starting from the first one. It's so simple. All you need to do is check whether the next one you pick is going to form a cycle. If it creates a loop, drop it and go to the next one. So we start with 1 and 2. So we have taken 1 and 2 and we include it in the list of edges in T. So check whether n-1 edges have been chosen. Of course, we are just beginning, so we are going to continue. The next thing is we look at the next one, which is 3 and 4. If we choose 3 and 4, it doesn't form a cycle. So we have 2 edges that are standing, or 2 subgraphs that are standing parallel to each other. They don't form a cycle. So we can include 3 and 4 into T. So 1 and 2 and 3 and 4 has been selected. We will never come back to 1 and 2, 3 and 4. So we check whether n-1 edges have been chosen. No. So we look at 1, 8. Check if it forms a cycle. 1, 8 does not form a cycle, so we take it and include it into T. So what we are building looks like this at the moment. Next thing we look at 4 and 5. 4 and 5 does not form a cycle, so we include 4 and 5 into T, and this is what we have. We are building our spanning tree gradually. So we've taken this 4 and we are not going back to them. Check whether n-1 edges have been chosen or not. Not chosen yet. So we look at 2 and 7, checks if it forms a cycle. It does not, so we add it to T. So we have 2 and 7 here. And then again we look at the next thing there, which is 3 and 6. Check if 3 and 6 forms a cycle. It does not, so we also add it to T. And this is what we have. So at this stage, we are virtually taking all the vertices have been considered in the graph. We only need to do a little more work to close it, and then we have a spanning tree. Now let's look at 5 and 6. If we choose 5 and 6, which is the next item, it's going to form a cycle. Choose this one, and then we have a cycle, and that's exactly what we want to avoid. So we drop it. If we also choose 7 and 8, we get a cycle, so we drop it. Anything that will create a cycle, drop it. So 6 and 7, which is the next thing to consider, does not form a cycle, so we choose 6 and 7. By now you can see from the graph that we already have a spanning tree. But is this minimum? If we have followed the algorithm correctly, then we are definitely going to have a minimum weight spanning tree. So if you look at the list that we have here, all the items that are not chosen are written in red. After taking 6 and 7, the graph is complete. Now you should also consider the remaining edges and see whether they will form a cycle. So if we had taken 5 and 8, we would have just closed it, and that's a cycle already. It's not allowed. If we have taken 1 and 4, we would have closed it. It's not allowed. If we have taken 2 and 3, we would have closed it, so we discard the remaining last 3 items. So check if n-1 edges have been chosen and T exists. Of course they have been chosen, and the spanning tree does exist. So we output T and we end the algorithm. So what we are going to do is calculate the weights. See, we are confident that 93 is the minimum weight spanning tree. If you add everything we have together, so what we have here will be 12 plus 12. I think I should have used the weights to indicate instead of counting the number of edges we have done. So we have 12 plus 12, and then we have 14 plus 14, and then we have 15, and then we have 13 plus 13, and everything gives us 93. If you look at this graph, you discover that there are many other spanning trees in this graph. The way the graph is described is so connected that you can be able to actually remove several spanning trees from the graph. So why is it so? Can you check whether any other spanning tree in the graph is less than this 93 that we calculated? Give it a try. So when the weights are not distinct, there can be more than one minimum weight spanning trees in the graph, which will actually give us this 93 as the same weight. So in such condition, the output of the crosscast algorithm will depend on the ordering of edges that have the same weight. So we could have actually gotten another spanning tree that does not look like this and is also a minimum weight spanning tree. Why? Because a lot of the edges, the weight of the edges are duplicated. We have 14 here, we have 14 here, we have 14 here again, we have 14 here again, we have 12 here, 12 here, 16, 16, 15, 15, 13, 13. It's going to give us several minimum weight spanning trees. The only time in which you are going to get a unique minimum weight spanning tree is if none of the length or the sizes of the edges or the weights of the edges is duplicated. So next we are going to look at Prim's gradient algorithm. So the algorithm goes like this. The input is the set of edges in a weighted graph with n vertices. The output is either a report that the graph is not connected or the set of edges in a minimum spanning tree in the network. So here are the steps. Step 1. Select an arbitrary vertex of G and include it as a vertex in the tree. Let W be the set of vertices in T. A. If the disconnecting set, remember we described a disconnecting set before when we were talking about connectivity. So we say if the disconnecting set is empty, report that G is not connected. Otherwise, find the minimum weight in the disconnecting set. If this edge does not create a cycle in T, select it for inclusion in T. Otherwise, go to step 3. But if it does, discard the edge and repeat step 2. So step 3, if t has n minus 1 edges, stop. Otherwise, repeat step 2. It's also a simple algorithm. So we look at the same example which we saw before. We now want to obtain the minimum weight spanning tree in this same graph by using Prim's greedy algorithm. We start with vertex 1 and select edge 1, 2. Then w is equal to 1, 2 and t is equal to 1, 2. We remove it and then we have disconnected it from the graph. So the next we find an edge of minimum weight in the disconnecting set. If it does not create a cycle in t, select for inclusion in t. So if we take 1 and 8, it doesn't create a cycle with what we have already created. So we select it and include it. Now we have vertices 1, 2 and 8 in W, and then we have edges 1, 2 and 1, 8 in. We'll progress from there. If you look at the graph we have on this side, either 2, 7 or 7, 8 is an equal edge of minimum weight. Both of them are 14, 14, so each of them could have been selected from the disconnecting set. Both of them will not form a cycle, so you can select any one of them. So go with whichever one your mind chooses. We'll go with 2, 7 in this case. And then we have included 7 in our weights, and then our list of edges now includes 2, 7. Now, after you have selected 2, 7, if you select 7, it's going to cause a cycle. So in this case, you have two choices. Either you go to 8, 5 or you select 7, 6. Both of them are edges of the same weight. So the choice is up to you. In this case, we select 5, 8 and then we include it. We now have 8 in the list of vertices and we have 5, 8 in the list of edges. We are growing our tree. So the next thing we are going to do is, if you look at this graph now, we are in 5. We have 13 here and we have 14 here. The obvious choice is to select the edge of minimum weight. So we select 4, 5 and we have now included 4, 5 in T, and we have included 5 in W, the list of vertices. We only now have 2 vertices left to complete our minimum spanning tree. So definitely from 4, where we were before, if you select 1, where are we going? You have only 2 choices, either to select this edge or select this edge. Now this edge is going to form a cycle, so it's a no-go area. The only choice we have now is to select 3 and 4, which gives us this. So we have now included 3 in the list, and then we have 3, 4 in the list of edges in the spanning tree. So we are left with one choice, and if that last choice does not form a cycle, we are going to select it. So we select the last choice, which is 3 and 6, and then it's complete. We stop the algorithm because we know that every one of the vertices has been selected. Now if you calculate this minimum weight spanning tree, you will discover that it is also equally 93 like the previous one we did. So because this side is 15 and the other side is 15, we could have selected either 8, 5 or 7, 6. It still gives us the minimum weight spanning tree. So this is Prim's algorithm, which is the direct version. Next, we are going to look at the matrix version of Prim's greedy algorithm, and it's still going to give us the minimum weight spanning tree. For simplicity, we will assume that the graph G is connected. Of course, if the graph is not connected, we cannot find the spanning tree. So let D is equal to Wij be the adjacency matrix. Which element is blank if there is no edge between I and J? Definitely this is an adjacency matrix. We are going to delete all elements in the first column of the matrix and mark row 1 with an asterisk. So we start with vertex 1. Initially, all elements are encircled. After creating the matrix D, each iteration has 2 steps as follows. Now the first step is to create the matrix. This is not the 2 steps we are talking about. I mean, after creating the matrix, there are other 2 steps. So these are the next 2 steps. Select the smallest element from the encircled numerical entries in the rows that are marked with an asterisk. Stop if no such elements exist. The edges that correspond to the circle entries constitute a minimum spanning tree. Step 3. If Wij is selected, circle the ij entry in the matrix D and mark row J with an asterisk. Delete the remaining uncircled elements in column J and go to step 2. Now, these things are not very easy to understand when you are looking at it the way the algorithm is written. However, an example will clear it off. So, let's see the third example. We are still using the same graph which we used before. We are going to obtain the minimum spanning tree in the graph below. This time we are using Prim's algorithm matrix version, the way it has been described in the previous slide. So first thing we do is create the adjacency matrix, and if you still recall the class where we learned about adjacency matrices, which is on graph connectivity. So the adjacency matrix is created like this. If you have 8 vertices, you are going to number the vertices 1, 2, 3, 4, 5, 6, 7, 8, and also on top here is 1 to 8. So normally the adjacency matrix, the way we described it before, is we start with 1 1, which does not have a link, doesn't have a loop, so we have a blank here. But from 1 to 2 there is an edge, which is this 12 we have here. From 1 to 3 there is no connection. From 1 to 4 there is a connection. So I'm not going to go through the whole process here again. If you don't follow this, then you have to go and learn about adjacency matrices in the topic on graph connectivity, previous topic. I think it is the third lecture, the second or the third lecture in this series. So let's say we already have the adjacency matrix, which is step 1. We will never go to step 1 again. So the main part of the algorithms is just a repetition of steps 2 and 3 until we finally get our minimum weight spanning tree. So first step is to delete all elements in column 1 and mark row 1 with an asterisk. So we deleted all elements in this. This is column 1. We deleted all elements. Then we mark row 1 with an asterisk. Next thing is the smallest uncircled entry in row 1 is 12. See, row 1 has 12, 16, 13. The smallest element will be circled, and delete the remaining entries in that particular column. And this is what we are going to be doing repeatedly until we finally get the minimum weight spanning tree. So once you circle the smallest entry in this asterisk row, you now delete every other thing in that particular column. We'll be doing this step by step. So take note that we are dealing with column 2. So since we are dealing with column 2, we now mark row 2 with an asterisk. You can guess what we are going to do next. So we marked 2 rows. Out of these marked 2 rows, which of them is the smallest entry between these 2 rows that are marked? So we are going to repeatedly look for the smallest entry in every asterisk row and we circle it. So since between 14 and 13 is the smallest, we circle 13, and the moment we circle something, we delete every other thing in that particular column. And you can guess what we are going to do next. Since this is column 8, where are we going to asterisk? Certainly row 8. So we asterisk row 8, and then we'll move next. So among all the asterisk entries, we've taken 13. This one is 15. Between 15, 14, which of them is smaller? 14 is the smaller. So anyone we have already circled before, we don't need to go back there again. So among all the asterisk rows, we have 16 here, we have 14 here, and we have 15 here. So the 14 is the one we are going to circle, and that is in column 7. So after circling 14 and deleting every other thing in the column, what are we going to do next? We are going to asterisk a particular row, And guess what that row is? That should be row 7 because this was column 7. So let's move ahead from there. Now we are going to look again at all the asterisk rows and see which is the smallest one that we have not previously circled. That is 15. So we circle 15, this is row 7, and then we delete everything in this column. And this is column 6. So can you guess which row we are going to asterisk now? Definitely row 6. We'll move ahead from there. Among all the asterisked rows and the ones that have not already been circled, which one is the smallest? 14. So we are going to circle 14 and delete everything in column 5. And which row are we now going to asterisk? Row 5, of course. And we'll move ahead from there. Among all the asterisked rows, smallest entry is 13. So we are going to circle 13 and delete every other element in the column where 13 is, and that is column 4. So which row are we now going to asterisk? Row 4, of course. We'll continue from there. Iteration 7. Now the next smallest element in the asterisk rows is 12, and that is exactly the one that we are going to circle. And this is in column 3. We delete everything in column 3, and the next thing we are going to do therefore is asterisk row 3. So when all the rows have been asterisked, every other element has been deleted except the circled elements, you can see that we already have a minimum width spanning tree. So the circled entries corresponds to the edges of the minimum width spanning tree, which is 14, 13, 15, 14, and then when you sum everything together, you actually get the same 93 which we calculated before. So the weight of the minimum spanning tree is the sum of all the circled entries in the last matrix, the final matrix that we have here. So before we go, we are going to look at Visual Studio Code and see a Python programming example of how to calculate the minimum weight spanning tree directly from the same graph. So here we are in Visual Studio Code, and we have a program called min span tree 0 to demonstrate the minimum spanning tree in NetworkX. We import TOS and do CLS because we'll be writing some things to the screen, and as usual we import NetworkX and we import math.lib as PLT. So we are going to get the current directory because we put the data for the graph, exactly the graph we used in the presentation. We put the data in a file, and the name of the file is min span tree.edgelist, an edgelist file. So before we go any further, I'm going to open that file so we can see the content. I want to change the font of the document so that we can see everything more clearly. So this is our description, graph description here. We have the name of the file here, and then we have source, target, weight. So the source are the two vertices that form the edge. This is an edge list, and these are the weights, as we see. So we'll go back to the program. So in order to create the graph, we just said G is equal to nx.read weighted edge list, and we use the file name. If you don't know how to do this, then please watch our previous videos. Every class has an example program, so you follow it step by step and everything will become clearer. Now what we are trying to do here, we've done it in the previous class before. We try to position the vertices of a graph in exact positions on the Cartesian coordinate, the way it is in the presentation. So vertex 1 is at location x equal to 4, y equal to 6. Vertex 2 is at x equal to 4, y equal to 4, so and so forth. So there are several ways to do that. You can plot using several figures to show the two graphs in two windows. For instance, what we'll do is first of all plot the original graph, and then after calculating or solving the minimum spanning tree using NetworkX, we'll now plot the spanning tree. So two ways you can do that is either to plot two different graphs or use subplots. Here we are using subplots. We already have example programs that demonstrate this, so if you don't understand, please watch the previous videos. So we'll draw the network nodes and draw the node labels separately, and then here we'll try to extract the weight from the graph. The previous tutorial video, the class before this, explains all of this in detail, so I may not go through all the details again. You can watch the previous class. Okay, so we extract the weights here, and then we set a counter variable k equal to 0, and then we are going to draw the edges, the edge labels, draw the edges and the labels of G in a for loop. So this print edge here is just for the purpose of learning. Everything you see here has been explained in the previous video, so if it is not clear, please watch the previous video. And then we'll draw, first of all we'll draw the edges, and then we'll draw the edge labels. So the first plotting we have done is for the original graph itself. The next thing we are going to do is obtain the minimum spanning tree. This is the new thing we have not done before. Since we have our graph G, it is so straightforward to use NetworkX to obtain the minimum spanning tree, and the algorithm in NetworkX uses crosscars from my research. You can check it out. Which algorithm does NetworkX use for minimum weight spanning tree? If you type that in Google, you should be able to get some information to confirm for yourself. So we'll create another subaxis, subax 2. We'll give it a title, minimum spanning tree of G, and then we'll draw. We're also going to extract the weights so that we can draw the edges together with their labels or their weights. Finally, we show the plot. So if we run this program, so this is what we get. Now you see that the minimum weight spanning tree corresponds to one of the ones we got in the presentation. So it's quite straightforward to use NetworkX to obtain the minimum weight spanning tree of a graph. So we have come to the end of the class today. Our bibliography remains the same: the book of Balakrishnan, the book of Edward Platt, the book of Philip Mensah, and other study materials. Be sure to check on my YouTube video tutorials. Please like, share, comment, and subscribe for more videos. Thank you, and see you in the next class.